I'm Eric Scheidley, and this is Astronomy Fundamentalized, Lecture 1, Alien Life. In this lecture, I'll follow a modified form of the Drake equation as we try to understand what science can tell us about the possibility of alien life in our universe. I don't have any pictures of aliens. That would end this really quick. I would just show you a picture and say, boo, there they are. Not only do I not have any pictures, but I don't have any experimental evidence of any kind. There's no legitimate scientific evidence out there, despite the fact that there's a lot of pop cultural sort of evidence. There are a lot of accounts of alien abduction that have inspired a lot of made-for-TV movies and so forth about alien encounters. But the blind truth of it is that there's no scientifically valid experimental evidence to suggest the existence of aliens at all. I have to say that and put that out up front. So in order to keep the interest of the thing and to keep that element of fantastic wonder, throughout the lecture I've included paintings by the artist Michael Whelan. Michael Whelan does paintings for the covers of science fiction books and fantasy books, the kind that I read when I was a very young man and certainly contributed to my taking up a career in science. So you'll see those paintings in here. If you're interested in them, they're available at glassoniongraphics.com. But anyway, this is where I get pictures of aliens from my imagination. But if I want to discuss real aliens, I can't talk about the kinds of aliens or all of the kinds of aliens that I see in science fiction films. For example, in the film Aliens, those aliens that went chasing Sigourney Weaver around a spacecraft have acid for blood, and they can live in outer space. There's no biology on Earth that I know of that can survive that. Certainly, my imagination can conjure up such creatures, but they've never expressed themselves in the biology of Earth. And so scientifically, I can't consider those things. I only can consider the biology that I know about. And so the aliens that I imagine are aliens that would be at least comfortable living with us here on Earth. In order to understand this better, I'm going to apply the method of analysis. And I went to dictionary.com in order to get a definition of analysis just for this purpose. And what I got was the separation of an intellectual or material whole into its constituent parts for individual study. And I'm pleased to see the intellectual part in there, because most of us think of analysis as I'm doing some crime scene investigation. I get this substance that I need to identify, so I send it to a chemist. They do some chemical processes to it. They discover its atoms and molecules, what it's composed of. They break it down into its constituent parts. Well, that's a physical analysis. Here we're going to do an intellectual analysis. We're going to take a question that we can't answer, that we don't understand, in the same way that we don't understand a mystery material. And we're going to break it down into smaller pieces that we may understand better, and thus, when we put it all together again, have a better understanding of the whole. It's surprising. It was surprising to me the first time I found out that speculation about life on other planets started as early as 300 BC. Plato himself wrote that if there's life here, then there should be life elsewhere, and he indicated the heavens, even though at the time when he was writing about it, there was very little understood about astronomy. It had only recently been discovered that there were planets that could be observed in the sky that wandered around independently. But since then, mankind has been, to at least some extent, fascinated and obsessed with the idea of there being life elsewhere in the universe. And it's not surprising, because the study intersects and involves physics, biology, chemistry, sociology, archaeology, theology. All of these aspects of human intellectual endeavor in some way intersect with the notion of there being alien life elsewhere in our universe. But when it comes to answering the question, lack of understanding of the fundamentals involved, that is, lack of understanding of the science, is what leads us to doing the method of analysis, so we can improve our understanding of even our understanding of the question involved. So if I take a material whole and I want to break it down to its molecules and atoms, I take the intellectual whole, which is a question. Is there technologically advanced alien life in our universe that might contact us? That's the question. I'll break it down and analyze it in the context of smaller questions that I might be able to say something scientifically about. The first of those questions is, what is the likelihood that other Earth-like planets exist in our universe? And if I find those Earth-like planets, what is the likelihood that life is going to develop on those planets? Life doesn't necessarily have to be there, but it could be a planet where sometime in the future life will develop, or perhaps in the past life had developed. If there's a planet with life, what is the likelihood that that life that exists on that planet is going to develop intelligence? And given that intelligence, what is the likelihood that technology is developed by that intelligence? Given technology, what is the likelihood that that intelligence would contact us or us them? Doesn't matter whether I mean accidentally or intentionally. Would we be able to detect each other, be able to recognize the existence of each other, be able to verify once and for all whether or not there's alien life in the universe? These are the questions that we're going to attempt to answer. None of them has an exact yes or no answer. Not one of these questions has been definitively answered. However, we can address them in a scientific way, and that's an important part. When we answer the questions, we have to make sure that we keep grounded in science. We can't talk about anything that is not experimentally verifiable. That way, when we can draw conclusions at the end, they'll be scientific conclusions and not fancy or whimsy or just wishful thinking about the presence of alien life forms. Also, we have to appreciate the fact that every time that you make some kind of a measurement, even if you make it with the most precise instrument available, that measurement has associated with it an uncertainty. Even when you measure to find the answers, you don't actually have the answers. You have to answer and then state the extent to which you're sure about the measurement. Even things that we take for granted every day, like the mass of the hydrogen atom, for example, has an uncertainty associated with it. So the first question is, what is the likelihood that other Earth-like planets exist? One Earth-like planet exists, and that's Earth. But that's the reason why I make this statement. We cannot consider life that would evolve on planets that are covered with lava, or planets that are in the depths of space and freezing cold, because these are places where Earth-like biology cannot take place. In order to have a planet that's Earth-like, you need to have the right temperature and liquid water. Particularly, you have to have the right temperature so that liquid water exists on the planet. It's also true that you have to have carbon and nitrogen and oxygen and these things around for biological life. But it turns out that those types of elements are abundant in the universe. No shortage there. The real key thing is having a planet with liquid water to support Earth-like biology. The reason why I do this is because life on Earth is the only life that's known to exist in the universe. So I look out in the universe, and in particular here, this is called the Hubble Deep Field. It's an image taken with the Hubble telescope, and every speck of light that you see in this image is a galaxy. In fact, the current estimate is that there are about 600 billion galaxies in our universe. Each one of those 600 billion galaxies has, on average, 600 billion stars. So if I'm going to search the universe for alien life, I have a lot of places to look. In order to get our minds around the thing and make it a little bit easier to manage, for the purpose of this discussion, we'll consider only life in our galaxy. Our galaxy is a little bit smaller than typical. It's a spiral galaxy of about 400 billion stars. So from now on, I'll talk about life in our galaxy alone, and any numbers that I state, in order to understand what the consequence is for the universe, you simply take the number and you multiply by 600 billion. So there are 400 billion stars in the galaxy, and maybe we'll go around and look at each one of them in order to check for alien life. Well, it turns out that would be a colossal waste of time. Because if you go outside and look up into the sky and see the individual stars, they're not the single points of light they seem to be. In fact, 50% of those stars that you see up in the sky are in fact what we call binary star systems. Two stars, one orbiting about the other. As you can see here in these two comparative telescopic images. The first on the left is from a ground-based telescope. And the star seems to be a single point of light, only slightly misshapen. But if we look at the same star from the point of view of the Hubble Space Telescope, which of course is in orbit around the Earth and outside of the Earth's atmosphere and therefore not affected by all of those influences, and certainly a very powerful telescope in its own right, we see that this is in fact two distinct separate stars. Well, the thing about that is, in order for a planet to have a stable orbit around a binary star system, it would have to orbit at a very, very great distance, a distance so far that the temperature would not be appropriate for liquid water. And so any planets that would exist in orbit around a binary combination of stars are not going to have Earth-like planets. It can be discounted. That means that of the 400 billion stars we know of and sort of have in the galaxy, that only 200 billion of them could potentially have planets that would be Earth-like. Here's an example just to show you the sort of measurements that we can take. This is actual depiction of the orbit of Ursa Majoris, a binary star system, and you can see over the course of a month or two the motion of the one star in the vicinity of the other. This is a very, very dynamic interaction between these two stars and not a very hospitable place for planets. Nevertheless, other stars do have planets. I don't think that the average person walking the street knows that we have already discovered hundreds upon hundreds of planets in orbit around stars other than our sun. It's very, very easy to find planets in our solar system, particularly the ones that are very large. Stars that have planets like Jupiter around them are influenced so much by the orbit of the planet that they wiggle back and forth in a very distinctive way that makes it possible to detect the existence of those planets. So other stars have planets, without doubt. How many of those planets are Earth-like is another question. Because remember, in order for a planet to be Earth-like, you have to have the right temperature so that you have liquid water. And this is the part where the mass of the star in question comes into issue. Because stars that have masses much larger than the mass of our sun burn very hotly, which is good because it means there's abundant energy available to provide the liquid water and life as life on Earth. But the trouble with that is that stars, like the one depicted whose lifestyle or life cycle is depicted on the left-hand side of this diagram, burn for only about 8 million years. Since it took at least 4 billion years for life to develop on Earth, any planets that orbit a star whose lifetime is only 8 million years, ending in a spectacular explosion of a supernova, are not stars that have planets that could be considered as Earth-like. So we have to make sure that we don't include any high-mass stars, but there's also a problem with stars that have masses that are much lower than the mass of our sun. Stars that have masses much lower than our sun burn very coldly. So in order to have the right temperature, a planet would have to orbit very close to the star. This causes a problem in that the planet would become tidal locked to the star. What this means is that as the planet rotates in its orbit around the star, as years and years passed, the rotation of the planet would decrease until ultimately the planet would show only one face to the star. That is, one side of the planet would be perpetual day, and the other side of the planet would be perpetual night. So even though the planet might be in an orbital position where its temperature would be ideal, it would have two extremes. One extreme, all of the water would vaporize and be blown to the other side of the planet, where at that extreme it would freeze out. And so there would be no available liquid water on such a planet, and so no Earth-like biology, and so that those planets don't count. We have an example of this behavior in our own solar system in that the moon that orbits the Earth, is phase-locked. It shows the same face to the Earth always. It's like the moon is a cameraman in its orbit around the Earth, and as it goes around, it constantly shows the same face. It wasn't always this way. Due to tidal forces, the Earth has over time worn down the orbital rotation of the moon until it has this property. There is really no dark side of the moon, as Pink Floyd would have applied. In fact, every point on the surface of the moon ultimately has daylight, and in fact, there's a sunrise and a sunset on the moon. But observed from the surface of the Earth, the face of the moon that we see is always the same. So if we eliminate all of the planets out of the 200 billion that are left, if we eliminate all of the planets whose mass is too high or too low to have Earth-like planets, that's about 10% that have the right mass that are left over. And so now we're going to consider the uncertainty in it as we bifurcate into two separate directions. We're going to discuss this from the point of view of the optimist, who believes that in most circumstances the conditions of the universe favor life, and the pessimist who believes in most circumstances the conditions of the universe do not favor life. And we're going to follow along these two lines of reasoning in parallel as we go along, making sure to keep track of the uncertainty involved in our descriptions. At this point, the optimist would say that all stars that have the appropriate mass have planets. And that's a pretty safe bet because we notice that planets are abundant in the stars that we've looked at near Earth. And so chances are that the optimist has a very good point in imagining that all the stars that have the appropriate mass also have planets orbiting them. The pessimist might say that planets are less common, as we might think from our initial cursory examination of our neighboring star systems, and so that only 10% of the stars that are left actually have planets around them. We have to wonder about those planets, the ones that orbit stars that have the appropriate mass and are potentially Earth-like. What are the chances that there's going to be liquid water on a planet even if the temperature's right? This is a picture of the surface of Mars, and the blue color that you see is a false color that's added to a certain depth of this cratered region on the surface of Mars. And what we see is something that looks vaguely like an ocean, or vaguely like a Rorschach ink blot. We could argue either way about whether it indicates that there was once an ocean there or not. But the interesting feature is the narrow band of, or the narrow valley that connects the blue crater at the top of the image to the blue ocean in the southern part of the image. That line is indicative of a river. Now, maybe it is or maybe it isn't, but it's the kind of formation that we expect when water flows across the surface of Mars. And so we sent one of our rover probes to this landing site for this particular reason, because we suspect that there was once water that flowed over the surface of Mars. And not only that, but about 2 years ago, the Mars Global Surveyor was passing over the surface of Mars, and in one orbit suddenly discovered the seemingly almost instantaneous appearance of an ice sheet on the surface of Mars. It wasn't there on the first pass. On the second pass, it was there. Big sheet of ice down the side of a crater. Where did it come from? Well, the speculation is that liquid water erupted up onto the surface of Mars while the surveyor wasn't looking and froze on the surface. That is sort of a controversial point of view or controversial theory about how that process happened. Nevertheless, it's a strong indicator that there may even now be liquid water under the surface of Mars, liquid water spontaneously created. So in our solar system, there are at least 2 places with liquid water, and in fact, there are 3, because Europa, one of the moons of Jupiter, has ice over its entire surface, but under the ice surface is liquid water. Water is kept liquid despite the fact that Europa has no atmosphere to maintain a high temperature. Well, it has a thin atmosphere, but not like Earth to act as a blanket to hold the heat in. There are geothermal, I guess it's legitimate to say geothermal events underneath the ice that are providing the heat to keep the water liquid. It's not hard to imagine that life forms could live there, like the ones that live deep in the ocean around the geothermal vents under the Pacific, around the Pacific Rim and the Pacific Ocean. So there are at least 3 places in our solar system where there's liquid water right now. So we wouldn't be surprised to think that the optimistic view is that all good solar systems that have planets have water. That since we have our solar system here and we have a whole bunch of planets and 3 of them have water, that it's so likely that the optimist is going to say that all good solar systems have at least 1 planet that has water. The pessimist is going to say that this is just sort of a coincidence in our solar system that there are 3, and in fact it's far less likely that you're going to have liquid water on planets, and say there are only 10%. That out of all of the solar systems that could have an Earth-like planet, only 10% do because of the absence of liquid water. So at this point, if we take stock of it, the optimist is saying that in our galaxy alone, there are 20 billion Earth-like planets. 20 billion Earth-like planets in our galaxy alone, where the pessimist, who has been extraordinarily negative, is saying that there are 200 million Earth-like planets in our galaxy. Even being pessimistic, it would seem that there are a lot of planets out there that have liquid water that could potentially support biologies like the biology that we have on Earth. So you have a planet. The planet has water on it. What's the likelihood that you're actually going to have life arise there? It's an extraordinarily difficult question to answer because we don't know how life arose on this planet. It is not known to science at the day of me giving this lecture. It is not known to science how life arose on Earth. That's not to say we know nothing about it. It's a very interesting question that's rigorously studied by biologists, biochemists, paleobiologists, trying to figure these things out. One of the things that we've learned is that if you take the contents or the recipe of the primordial atmosphere of the Earth and you stick it in a jar, and you zap it with some lightning, and you put it in an oven, you bake it at the appropriate temperature. This jar that's filled with carbon dioxide, nitrogen, and argon, and water, various minerals that are available in the primordial Earth, just after its formation as a solid object, some 4.6 billion years ago. You cook this thing up in the oven, and you take it off, and you send it to the chemist for a chemical analysis. The chemist doesn't come back and say that it contains water and carbon dioxide. No. Comes back and says that it contains nucleic acids and amino acids and all of the building blocks of the biology of life on Earth. Not life itself. You don't open the jar up and little people come out. It's absurd. Nor do you even get cells. No one in a laboratory has succeeded at this point to create living cells from nothing. But you do get all of the building blocks of life. So we know that our origin, in terms of our chemical composition, is easily created. We don't even have to be a careful experiment. You could do it in your kitchen. Easily create the building blocks of life. Now, where the life comes from after that is difficult to say. Nevertheless, the optimist would probably say that since it's so easy to create the ingredients of life, then it's probably certain that life is going to develop on other planets. The optimist is being very optimistic. The pessimist is likely again to say that only 10% of planets that have water and all of the ingredients necessary to life will ever develop it. And the reason for that pessimism is that chemistry is a delicate balance of interactions between molecules and conditions and temperatures and so many different factors. And since we haven't been able to identify the trigger that is the creation of life arising on this planet, then it would that in itself, the fact that we have not easily done it in the laboratory, implies that it is not easy for that to happen in any sort of natural way. So the pessimist once again says that it's only 10%. So taking stock, the optimist is saying that there are 20 billion planets in our galaxy alone, 20 billion planets, where life existed in the past, exists now, or will exist in the future. And the pessimist is saying that there are only 20 million planets with life on them. The pessimist, who has been extraordinarily negative, is saying that in our galaxy alone, there are 20 million planets that have life. Remember, as we go through this, that that's in our galaxy alone. If I take the pessimistic view of 20 million planets with life, and I want to understand what that says about life in the universe, I have to take 20 million and multiply it by the 600 billion galaxies in our universe. So now I have life on a planet. What is the likelihood that life would develop intelligence? If intelligence means the ability to solve problems, then no doubt about it, life has developed on Earth. Not only has it developed in human beings, but it's also developed in a large number of creatures. Primates immediately come to mind, but they're related to humans. But we'll skip right to dolphins. Dolphins clearly are very intelligent. So are many octopi. So are squirrels are very clever. They can get into the bird feeder no matter what. Dogs are very intelligent and can solve problems. My dog, who's named Kepler after the astronomer, is not particularly bright, but I've seen dogs that are very intelligent and can solve problems. So intelligence has definitely developed on Earth. And it's really not surprising when you consider a concept from you may have learned about in your biology classes called biological convergence. The idea here is that if there's a trait that an organism can have that's useful for survival, that trait will appear more than once. And a good example of this that I can give is wings. Wings are extraordinarily useful property for an organism to have because wings can help you to avoid predators, to find food, and to find mates. All of these things very useful to continue the species. And wings have developed in birds, in insects, and in mammals, if you consider bats. Wings are so useful that they developed in these completely disparate species. This is because we view intelligence as a biologically convergent property. It's so useful that it develops. I would submit that intelligence is a biologically convergent property because how else can human beings survive on this planet? The reality is that without your intelligence, you stand little chance against lions. A human being is slow and soft and takes almost 20 years to rear its young. Lions would have a field day, were it not for the ability of human beings to sharpen sticks, build fires, build shelter, and so forth. Also, we can't survive the elements in most areas on the surface of this planet. So in order to be successful, it was a requirement that mankind develop intelligence. So the notion of biological convergence gives the optimist the position to say that intelligence is a certainty. There's so much intelligent life on Earth. It's a biologically convergent property, so if you have life just based on the need to survive, intelligence is likely to develop. The pessimist is going to say 1 in a million, not the 10% that the pessimist has been saying all along. And the reason for that is that at the end of the Cretaceous era, the Earth was dominated by the dinosaurs. And the dinosaurs were keeping the mammals at bay. In fact, at the time, the only mammals that existed on the surface of the Earth were small rodent-like creatures. The dinosaurs were the dominant species, and only through the intervention of an enormous asteroid that is believed to be the cause of the extinction of the dinosaurs did it make way for the small mammals of the period to continue to evolve and ultimately become the dominant species on the planet, human beings. So without that intervention, who's to say that the dinosaurs would not have continued to control all of the ecosystems of the Earth? So the pessimist says that it's a 1 in a million chance because there has to be some freak intervention that gives the intelligent species the upper hand against species that have more practical biological advantages. That being the case, the optimist now says that there are 20 billion planets in our galaxy alone where intelligent life exists or will exist in the future or has existed in the past. The pessimist is saying that there are only 20 planets in our galaxy that have intelligent life. 20 planets. Remember, in the universe, that would be 20 multiplied by 600 billion. So you have intelligent life on a planet, just like we have here on Earth. What is the likelihood that technology is developed by that intelligence? Well, it depends on how you define technology, certainly. Were it a discussion other than this one, I would say that the first technological advance that an intelligent species can make is the plow. The plow is an important technology to mankind because it made organized agriculture possible. As soon as you can spend your time in agricultural pursuits, you grow enough food to feed a community, and then members of that community no longer need to spend time searching, hunting, and gathering for food, and can use their intellectual power for other endeavors. And that is how the human race moved forward from simply being nomadic people to being organized, socialized, and technologically advanced. But for the purpose of this discussion, I would like to define technology as the ability to create and send radio signals. The reason why is that that technology is the first technology that makes an intelligent civilization in the universe visible. We created radio waves, started really broadcasting high power radio waves in the 1920s, 1930s. Those radio waves have traveled out into space and have reached hundreds of planets, and would be easily detectable because we make a spectacular amount of radio noise, much of it unintentional. Even if you take a comb and run it through your hair and generate static electricity and then wave it around in the air, you create electromagnetic radiation, you create radio waves. Your computer is creating radio waves. The lights in your home are creating radio waves. We use radio waves for entertainment, we use them for cooking, we use them for radar, we use them for all kinds of communication on the surface of the Earth. So we're making a spectacular amount of radio noise that should be detectable. We are a radio sophisticated, technologically advanced civilization. By the way, here in the picture we see an artistic version of a radio telescope, and then the inset picture is an actual photograph of the Arecibo radio telescope in Puerto Rico. It's about 3 football fields wide. It cannot be moved. It relies on the rotation of the Earth to get look at different areas in the sky. The triangular section in the middle that's suspended from wires is actually the receiver. Radio signals from outer space bounce off the dish and up to the receiver when they're there and interpreted by computers, and scientists use that information to understand all kinds of information about stars and nebulae, globular clusters and quasars and things about our universe, but also to use that data for the search for extraterrestrial intelligence. So there's definitely intelligent, technologically advanced life on Earth. So the optimist would say all intelligent life develops the ability to send radio signals, because it's awful clever of us to have done it in the first place. And at this point in the lecture, I'm always reminded of a novel that I read by Kurt Vonnegut, and I can't remember which novel it was. But Vonnegut said that the human race, I think Vonnegut was often very concerned about human pride, but he said the human race is awful uppity, who only 400 years ago discovered that their planet had another side to it, and that the best course of action would be to go and kill everyone who lives there. We've only been technologically advanced for a few hundred years, and yet the optimist is going to say that intelligent life develops the ability to send radio signals with absolute certainty. I would say that an immediate argument against this is that some of the intelligent life on Earth doesn't have the capacity to. For example, dolphins, even if they're more intelligent than we are, can't develop this technology because they don't have hands. In the absence of opposable thumbs, they can't do the fine motor manipulation in order to produce sophisticated enough technology to create radio signals. So they just blithely swim around in the ocean, enjoying themselves, without the development of technology. And perhaps in many ways they're happier than we are, but we are the technologically advanced species here. So the pessimist says that you need the thumb, and so there's a whole bunch of intelligent life on the planet, but only we accomplish the radio signals. So maybe only 10% develop technology, and by technology meaning the ability to send radio signals that we might detect from here on Earth. Here's a signal that we deliberately sent out in space using the Arecibo telescope. The sequence of ones and zeros that you see here in the image is a binary code. It's the code that would be most easily translated by an alien civilization. And in the middle, the black region that looks all sort of Atari is the graphical image interpretation that you get once you've broken the code. The first line, starting from the top and working our way down, is a description of our number system. So that we can establish with the aliens how we enumerate things. And then the next thing is a very, very small portion of the periodic table. In particular, it gives the elements that are necessary for human life. The next step down is the formula for the sugars and bases and nucleotides of DNA. And then the very next thing is a sequence, a DNA sequence. This part has always made me a little bit nervous, because we're beaming out into space to aliens, basically instructions on how to kill us. But I guess that's me being the pessimistic view of the thing. But the next thing is that we have the height of a human being. It's given in hydrogen atoms, because that's the only way we can have a distance scale in common with aliens. We tell them that we are in fact the third rock from the sun. We see the planets, including Pluto, distributed, and the Earth jumping up there. And then we see this curved hemisphere with what looks like an M underneath of it. This is actually a depiction of the Arecibo telescope. It's us effectively giving our phone number to the aliens, saying this is how we'll detect you if you send a signal, and so they could tailor the signal to be detected by the Arecibo telescope. We've beamed this message into space at very high power, and by now it's reached hundreds of worlds. And we have, as of yet, not received a reply. So at this point, the optimist is saying that there are 20 billion planets in our galaxy alone with technologically advanced life that is currently in existence, will exist in the future, or has existed in the past. 20 billion planets in our galaxy with technologically advanced life, where the pessimist, who has been extraordinarily negative the entire time, estimates 2 planets with intelligent, technologically advanced life in our galaxy. Now remember, that number 2 gets multiplied by 600 billion, which means that the pessimist imagines that there are 1,200 billion planets in our universe that have technologically advanced life. Of course, the technologically advanced life on the other side of the universe we don't have access to, because even if they're creating radio signals, the amount of time it would take for those radio signals to travel to Earth is fantastically large, and we wouldn't have received those signals yet. So if there's that technology exists, what's the likelihood that they're going to contact us or us them? The fact of the matter is that our estimate shows that there should be technological life around somewhere, but the fact of the matter is that we have not seen no evidence as of yet of the existence of any technological life. And that's not to say that we're not looking. And in fact, there is a tremendous scientific endeavor going on in order to discover the existence of alien life in our universe, and it is no longer, if it ever was, the job of crackpots and discredible scientists to do that sort of thing. There is the Search for Extraterrestrial Intelligence, which is an organization which is governed and supported and participated in by legitimate scientists from all over the world. It's an endeavor that they take very seriously, and you can visit them at SETI.org, the Search for Extraterrestrial Intelligence.org. And they have lots of articles describing the efforts that are being made to understand the potential of alien life and all of the biological issues and astrophysical issues and physics issues and associated with that. Not only that, but they have some software that they can provide that you install on your computer, and in the middle of the night your computer goes out on the internet and collects a little bit of radio data that was collected by a radio telescope, brings it back and analyzes it, searching for alien radio signals in it. It finishes that up, generates a report, and sends it back to SETI. The reason why they do this is that there's so much radio data collected by all the radio telescopes in the world that it is impossible for SETI on its own to dedicate the kind of computing power necessary to analyze the data. So they're having everyone's home computer help out, and imagine what it would be like if it was your home computer that actually discovered the aliens. It's a bit of a thrill. If you're interested in doing that sort of thing, you should go and check it out. But this is a search for extraterrestrial intelligence. And are we alone in the universe? I still have not answered that question. Nevertheless, I have discovered that from our current scientific point of view, it seems likely, almost to the point of certainty, that technologically advanced life exists elsewhere in our universe. Unfortunately, it also seems likely, perhaps to the point of certainty, that we will never contact us, that they will never contact us, nor us them.